afternoon to everyone. If you give me a moment, I'm going to share my screen. So with this today. Okay, first of all, I want to thank Optics for giving me the space. And then everyone to the participant here. And I left also here my email in case you want to ask me questions. And I know that Optics, they will post also the presentation. So there will be some links that may become useful to you. You can also check then the presentation after. For about a year, I'm honored to be one of the NASA Heliophysics Education Activation Team, led by Professor Ramon Lopez and Dr. Rebecca Vieira. The group created material to teach physics in the context of astronomy. And in particular, as ambassador, and also the group themselves, they encourage high school or colleges or university to adopt some of this material. At the end of the workshop, I want to share with you where you can find the material, and also some information in case you want to become an ambassador for this new year cycle. So physics in the context of astronomy. Therefore, the main characters for us will be today the sun and the earth and their interactions. The plan is to do the workshop together, then show you the website with the NASA HEAT activities, and then I'll tell you just a little bit of my experience with the team in the Chicago. So I'm using one of the activities prepared, and I like to share it with you. I'm going to place in the link this one here. The activity is exactly the same as the one that the group wrote, but I just added a few spaces for my student in case they have to draw. And I had also one schematic of a reference frame where the student need to complete it. But
Francesca, I just wanted to, sorry to interrupt. It looks like the link you put in the chat is the Zoom link.
Oh, so wait. Copy link address. Let me see. Thank you. I'm sorry about. Yes, that should be the one. The second link. Does it work?
Yes.
Okay, thank you. I appreciate it. Now, let me see 1 second. I would like to start in the same way that I do it with my student. And it is with first, I tell them, and just give me a second. Grab your phone, your smartphone, or I just show my smartphone, and I use an app that is called Physics Toolbox Sensor that was developed by Christian Vieira and also other member as a consultant of the group NASA HEAT. And this app, like also another app that is called the FIFOX, they take advantage of the magnetometer that are on the phones. Not only magnetometers, other sensors like accelerometers as well. But for the magnetometers, and this app in particular can give us the vector magnetic field. So I tell my student, here, yes, Sanhita said that she's using these apps in her class. Yes, they are useful. And just take out the phone, measure the inclination of a plane, or check what is the magnetic field of the Earth. So here I show them maybe this picture, or just they all look at their phone, to point out that first, of course, the Earth has a magnetic field around it. And second, that this magnetic field is a vector, that we can visualize it like that, with an X, a Y, and a Z component. And then I say, now in this tutorial, you will pretend to be a scientist living in one observatory in Alaska, in this case, and checking, like you're doing right now, what is the magnetic field of the Earth. And sometimes, because of the interaction between the sun and the Earth, we will see that in a moment, this magnetic field value and vector component can change. And they are due to current that they form in the ionosphere, about 100 kilometers from the Earth's surface. And like any regular wire with current, they have around them a magnetic field. But the next thing that I do with my class, after I said, pretend to be one of these scientists with your smartphone and checking what's the magnetic field value, and give me a moment that I want to share again the screen. I go into this website. Tell me if you see it.
Yes.
Okay. Not this one. Just a second. The website is connected with a NASA satellite, solar and heliospheric observatory. And from this website, we can see images of the sun. Even what is the sun doing today, for example. Because the tutorial is based on real data that were collected in an observatory in Alaska in 2017. So then I go back here in the year 2017. Then I pick November, and I pick the window between the 2nd and the 4th of November. And then I ask the page to generate images of the sun. On the SOHO satellite, there are instruments. One of them is called a coronagraph, and the coronagraph is shielding, like kind of creating an eclipse of the sun, so scientists can see just the corona around it. And then if we hit the play button, we see what is happening. In essence, the sun is always active, and depending on the day and the time, there is also a cloud of particles, charged particles, that is ejected from the sun together with a magnetic field. And this cloud of particles, this plasma plus magnetic field, may reach the Earth. And on the ionosphere may create beam of charged particles. This is what I would say to my student, that can be modeled as wires. And as I said again, a wire with current generate around it a magnetic field. So at this point, usually I start drawing. And if you don't mind, I will also draw. So I'm gonna go back to the presentation that I have here. And I have a blank page, and let's see if I can see the annotation. Okay, and on this page, just a second, that every time that I change, I lose the page, and I see instead the images. I'm sorry, I will be. Do you see the blank page? Oh, okay, that's good, because I don't. Okay, so. Just a second, that there are so many. This one I didn't find it anymore. Okay, I see it. I'm sorry. I am sorry. I found it. Okay, so I take to my class. Imagine the sun sending this cloud of charged particles toward the Earth. And then I draw the Earth. The Earth has a magnetic field. So I draw just a little bit of the magnetic field lines for the Earth. Magnetic field lines that are getting out from the north magnetic poles, and they are entering into the south magnetic poles, and then also passing inside the Earth here, the magnetic field lines. And this current are about at the height of the ionosphere, around 100 kilometers from the Earth's surface, as I was mentioning before. And they create around it a magnetic field. So here, start with the right-hand rule already. Like in my picture, I have the current pointing diagonally upward. This would be our thumb. So the magnetic field are closed loops around these wires with current that are also called electrojet.
Are all the particles the same charge?
Mostly when I did the activity, they were charged protons, but I would assume that they are also electrons from the sun, the plasma that is ejected. Imagine now the observatory in College, Alaska. And at that location, they are recording the magnetic field BX, BY, and BZ component. So here they have maybe the vector magnetic field. Now in this activity, we will know this magnetic field vectors component. We will work backward in finding the current. In particular, today altogether, we will have to find how much is the current in amperes. What is the direction of the flow of the current? And also, where is the location of the wire with current with respect to the observatory? If you don't mind, I want to share one more thing before we start, and that is this next slide. Hopefully, I will not lose it. This one. Recently, not long time ago, very recently, a NASA mission with Johns Hopkins Applied Physics Laboratory sent in space, 3 satellites, and the mission is called the EASY mission. You certainly have heard about it. And the satellites are collecting data of the X, Y, and Z magnetic field, this time not from ground, like the grid of the observatory, but from the orbit around the Earth. And I'm not gonna start the video, maybe, I don't know, but I put the link of this video and you can just watch it. Or what I did, because I did this activity recently with my class, I showed the video. It's not that long to my student. And here you see depicted the beam of charge, the plasma that is traveling and then forming the auroras at the poles in this part here. That's also image comes from the same video. One last thing, when I am in class, I bring some material. So student can also in some way build the observatory with its own reference frame and the magnetic field vector. So I'm using the material. This is an image that I show usually to my student about the actual observatory in College, Alaska. And here is the material: Play-Doh, skewer. Yes, a video link. It will be posted at the end the presentation. Yes, I have all the links. You're welcome. Yeah, it's a short video, and there are 5 facts about the EASY mission, and they explain everything clearly. So I was saying, skewer, Play-Doh. Yes, and same sticks for shadow activity. Ah, that's funny. To show the shadow of the stick.
Basically for sundials.
Oh, yeah, yes. Where I live, there is not far a sundial, and we are always going and check it. And it's fun. Like now we change the time and the sundial doesn't, right? Okay, so the sticks, for me, not sundials, but they are the X, Y, and Z of the reference frame. Then the bracelet, they are, guess what? The magnetic field. And I also put a toothpick as the tangent. And then the Play-Doh is the observatory. So first thing now, I would like to show you this I, J, and K. Maybe you don't have any of this equipment at home. Sometimes you can just use toothpicks. If you grab a piece of bread and you mash it, this could be the Play-Doh holding the reference frame, or just drawing with a pencil on a paper. So I'd like to start the very first page of the activity all together. Then I show you a couple of more slides, and then we will work on the activity, maybe divided in groups. So first, let me go into the page for the Aurora current. And here you have it, the tutorial. Obviously, together to put the student in the context of the sun, the electrojet, the observatory, we also review magnetic field, Biot and Savart law. So I also say, okay, remember that Biot and Savart is mu0 times I divided by 2 pi, and then R. I is the current, R is the distance between the wire with current, so for us the Aurora currents, and the place where it is measured. Also, I remind the student that this is maybe a symbol for into the page, and here maybe we have a wire of current into the page, and with the right-hand rule, we can figure it out what is the direction of the magnetic field lines around them, because this is all about of the activity. Okay, so I will read, and just the first question, I would like to do it all together. Imagine that you and a friend are studying magnetic fields by straight line current in a physics lab. You have started by defining a coordinate system in which the directions of due north and due east, both parallel to your tabletop, are defined as the I and J positive directions, respectively. And the question is, for all of you, and don't answer immediately. I always tell my students, don't answer immediately. Just think about it, and then you can put it on the chat or unmute yourself. Which direction should you select for the positive K so that your coordinate system is right-handed? Please explain. And then the note, which is important. Your answer here in this part may seem an odd choice, but we will see how this choice will be necessary when we examine the real data that are coming from College, Alaska, the observatory, about the Earth magnetic field. So again, think about it. You have maybe with you a pen or a pencil. Pretend one to be the x-axis, the north, the other the j-axis, the east. And yes, indeed, I see the answer already. Perfect, indeed. And that is very unusual, at least in my classes. Usually you do like this, but the reference frame that then has the positive Z pointing downward is weird. That's why with my classes, I ask them to bring the clay, and to build the observatory. And give me a moment, 1 second, that I'm gonna share the PowerPoint back again. So this is what we do. The classroom is the classroom where I usually teach physics, and we have the I, J, and the K pointing downward of the reference frame, absolutely. The Play-Doh, some of my students build the observatory here in green, like a roof. They made a nice, neat thing. Other students with the Play-Doh, they just keep it in their hand for the entire part of the activity. And I use the Play-Doh because at the end, they will have the magnetic field loop, the magnetic field vector, and they need to figure it out where is this vector on the, with respect to the observatory. What is the current with respect to the observatory? So thank you, Sanhita, for giving the answer pointing downward. That's perfect. I'm going to share back the in this page, I left some room because I asked my student actually to draw. And one note, sorry, activities prepared by the NASA HEAT group. They come in a format that is a Word document, so you can adapt them to your class if you want to just do a portion of it or all of it or divide it in 2 days. You can modify and adapt it. So now I think that maybe if Chris is okay with it, we can divide it. Maybe I'm going to read this part and then we can divide it in groups. Maybe I would say 10 minutes or so, something like that, or 15 minutes, where I will ask you please to try and answer this question, just this page that I have here, page number 2. So I'm going to first read it. And then, Chris, if you're okay, we can divide it in groups. What do you think?
Sure. Yeah, I'll set up 4 breakout rooms, so we'll have 3 to 4 people.
Thank you. Okay. So now imagine that you begin your experiment by setting up a long, straight wire so that it is oriented horizontally at a uniform height above your table, so that it carries a steady flowing current in the negative J direction toward west. When I ask my student, and if you can also here, I don't know, but when I ask to write on the skewer the coordinate I, J, and K, I also ask them to add whether it's north, east, because it is helpful. And then they will also have another skewer or a pencil, and that is the wire with current. The image on the left is like the plane of the table, which you can think of the plane of the observatory, tangent to the Earth. And the image on the right is a side view. So if you agree, we can divide and try, and then we come back. Maybe, I don't know, 10 minutes?
Sounds good.
Thank you.
All right. Rooms are open. So you should be able to just join a room.
Welcome back. And so anyone would like to share their answers for this location C, D, and E, just for this page? And you can put it on the chat, or Brian in my group was drawing it on the page. Or you can just unmute yourself as well. Or if you had any trouble.
Should I go ahead if no one else wants to?
Please.
Go ahead.
Okay. So as we discussed in our group, there's no field directly below the wire. And then the field at point D, I'm just reading from my notes, is BZ, and it's positive. Am I right?
And well, grab a pencil and point it toward the left, like here.
Yeah.
And
So this
your
is the
thumb,
current.
yeah, perfect, like that, perfect. Yes. So at the location C and the location E are exactly below the wire.
That's right.
And because the magnetic field are loops like this, Brian drew perfectly. Let me see if I can, in some way. You have a vector that is coming out of the page, also for E, coming out of the page. let me see.
If you take a perspective, it's like this. See, it's offset.
I can see it, yes. So your pen is the current, right?
Coming towards you. And
Coming
then,
toward me.
and then this is the field coming down. So
Mhm.
you have D offset from the wire. So it's going in like this.
And let me, I lost the pen. But if you look at C and E, the magnetic field is coming toward you, out of the page.
Mhm.
Correct, perfect. And then at D instead is diagonally pointing downward because the tangent over there. Let me share this. And now can you see my page, right? I think.
Yes.
Okay, thank you. So at C would be the magnetic field like this. At E is exactly the same thing. And my students really have the skewers. And at D is a little bit diagonally down, so it's harder. I will draw it on the side view here. C is like this. Magnetic field has only the X component. And at D, because you draw the distance, which would be the R, and then here the magnetic field at D. So this is BD, which has the X component and the Z component. The angle for the Bogdan says could be determined from the distances given. Yeah, for example, in class for this part, I don't stress too much to considering the 6 centimeters or by yes, because in the next page they will do it also. But yes, this is what they would need to do as well.
But that BX is along negative X, right? Just to be sure.
Yes, because this would be the I direction.
Oh, okay.
And in the side view, this would be the J direction. Therefore, we would have north here and east here. And the current is into the page, so it's going west. And the vectors at C, exactly as you said, Bogdan, has
Yeah, someone else, Brian also said that. Yeah, negative.
Sorry,
Yeah.
because my images are on the other.
It doesn't matter.
On the other screen. Negative, yes. So therefore, the Bx is negative, By is 0, and this one, Bz, is also 0. For the location E is the same thing as C. And for the location D instead, we have that the Bx is negative, By also 0 as above, but Bz is positive. And the last question, why one component is always 0? Anyone? I know you know, but anyone would like to share it, please?
So the magnetic field will circle the current carrying wire, and there will be no component of the magnetic field in parallel with the wire, parallel with the current.
Thank you. Yes, perfect. Thank you. Next. I'm gonna start by reading it, and then please, again, if we can divide it in groups, and then you can work on this next page. Then we can meet again to check that everything is fine, and then we do the other page. The aurora is created by electric currents from space that flow along the magnetic field into and out of the ionosphere. These charged particles move horizontally through currents called the aurora electrojet. Imagine now that you and your partners, working as a physicist at the U.S. Geological Survey, are reviewing magnetic field from data collected at the observatory in College, Alaska, that were taken on a day on November 3rd, 2017. Of a small magnetic disturbance. We have seen it on the SOHO images. It was just a tiny thing, like a tiny maybe CME that was ejected on the bottom right of the sun corona. The zero level in the plot below refers to the undisturbed magnetic field, so that the deviations from zero in the magnetic field are due to the aurora current, to the electrojet. The right-hand system is the same as we did in the previous page. X, Y, and the Z is pointing downward, which technically would be toward the Earth center. In this part, you don't have to use any numbers. Usually I tell my student, this chart show data that are directly taken from the observatory. And for all of you, the NASA HEAT group put a link to the site where the data are taken. And everyone actually can see the data. I show you, if you don't mind, a moment, just this website, which is this one. There is a grid of observatory all around the Earth, and they are collecting the magnetic field. While now this EASY satellite is collecting from above. And if you go, for example, here you see map. Here is all the observatories. And the one that gives the data is this one up here, College in Alaska. In this page, thank you, Chris. In this page, they also show which kind of instrument they are using to collect the magnetic field. Flux gate and proton precession magnetometers. If you remember, when I started, I said to my student, okay, let's grab our smartphones and check the magnetic field. The magnetometers that are on the phones, probably they use maybe Hall effect. Here in the College Alaska Observatory, they use definitely more accurate effect. On the EASY satellite, they are using Zeeman effect. So on this same site, if you go into, let's see, go back, data, downloads, and plot, you see the data also here. You have to select the particular town, like here, College USA, the date, and the data pop up. So let's share back the chart shows the X coordinate, the Y coordinate, and the Z coordinate of the magnetic field. The last plot sometimes could be, I looked at this website, it sometimes could be the difference of some vectors, sometimes is the total, but I always usually ask my student to look at the first free chart. Yeah, it is a good resource there. On the right side, there are the official values of the magnetic field of the Earth on that November 3rd, 2017. And then I suppose that the NASA group normalized them so that we see only just the magnetic field change because of the electrojet on the ionosphere. The group itself says just to consider for our purposes, we use only the data displaced in the first free part of the graph. So what I would like to do is a short, just one question. So maybe less than 10 minutes is good. Let's divide again in groups and let's try to answer this question. With your partners, explain how you can make sense of the magnetic field data at 12:30 Universal Time by approximating the Aurora current as a line current running along a west-east line in the ionosphere near the observatory. I added this sentence, no numbers are needed. The student, just from analyzing the chart, they should be able to say whether the current is running west or east, and explain also why it is so. And I also point out, because sometimes my students are not familiar with this, that the time on the x-axis is now 12 o'clock, and then here would be 1 o'clock, 2 o'clock, and 15 obviously correspond to 3 o'clock in the afternoon. But sometimes I notice that my students have a question in regards of the time here. Okay, if Chris, if you don't mind, we can just again divide ourselves for maybe 5 minutes or so. I don't know, something like this.
Perfect. All right.
Thank you. Just for this page.
Rooms are open.
Thank you and welcome back. Would you like to share what is your finding for whether the current electrojet is running west or east?
I have a question before we kind of address that, if it's okay. How do you know that, I mean, what evidence is there that this electron jet is an east-west line and not more a vertical line? Because, you know, when I usually teach about auroras on a conceptual level, not with data, you know, you talk about how the Earth's magnetic field kind of traps these ions so they don't get to the Earth. So the magnetic field is helpful. Yeah, except, of course, at the poles. So then I envision, and perhaps I'm mistaken, you can enlighten me, that the particles are coming in on the poles kind of like towards the center of the Earth and so they would be coming in more vertically, not east-west. So you're saying they're coming in east-west. Can you
Yes, maybe the best answer, if you don't mind, is to just see if Chris, are you okay with that? We can just see a couple of minutes of this video.
Of course, yeah.
Okay, just a second. That I think I need to. Share the computer sound. Okay, so in a first of its kind mission. Were you able to hear the sound? Thank you. Johns Hopkins APL sent 3 small CubeSats into orbit around the Earth to study the solar.
Can you make the sound louder?
The Earth's poles, central to the link between Earth and the surrounding space.
Its mission and scientific contributions are extremely high.
I think you have to share the audio, your Zoom will cancel out all that background noise so we can't hear it. I think you actually have to, in the video, say share audio with video or something like that.
Oh, I did it for the Zoom, so you were not able to hear it? Sorry. But then just let's look at this image here. This is a pretending image. Do you see the image?
Yes.
Okay, so imagine maybe the sun on the right side of the screen and the charged particles are traveling, and then the current are formed kind of parallel. Either here is not at the pole, but parallel to the poles and to the side here of the Earth. I suppose that the one that are going then down and creating the auroras are extra, wouldn't be? Right?
So
Because
the
this
direction, the white direction is all at the North Pole? Is that what we're seeing there?
but it is, well, it could be also like this one, for example. Wait, like this one. Here is the North Pole.
Uh-huh.
So the plasma is traveling toward the North Pole, forming a kind of parallel wire of current.
And so according to this picture, it's going from east to west and then it leaves? Ah,
In this one is, yeah, from the screen, from the right to the left. So, but then it's a simulation here.
But I
It's not
think
like-
we are supposed to notice, right, that there is no change in the magnetic field along Y, right? This is probably how we concluded it's east-west.
Yes, yes. For this activity, yes. But why they don't go spiraling? I guess then there are
yeah.
charged particles that are spiraling along the magnetic field lines, but the bulk of the electrojet is just traveling parallel to into the ionosphere. That's what I understood. That was the question that Nancy asked, right?
Yes, so you're saying that the aurora effects, these pretty pictures that happen at the poles, are something different than this electron jet, because we see the electron jet is not happening at the pole. So this is looking at something different. Are you going to then connect this to the auroras in the next part, I assume?
But wait, just a second. These are, I would assume, I may be mistaken, also some of the particles are then trapped into the magnetic field of the Earth, creating the auroras. Because we have the auroras always when there are these big activities of the sun. But the main flow is on the ionosphere and current flowing. That's my understanding. I can look at more, but this is how I understood it. Anyone has a...
So by looking at this graph, do you look at when it goes negative and look at the times, or what is it that I don't understand?
Okay, let me explain the graph. So they ask to look at the graph around 12:30, which is here.
Yeah.
So the Bx is going to be negative. Then the By, we can assume that is zero. Yes. And that, as I think Bogdan was saying, is already an indication that the wire that this electrojet is along the y-axis. And then the last component here, the Bz, is negative. So yeah. I want to draw a picture. Let's pretend that we have the geographical north on my right side here, and that would be the I direction. And then I'm gonna, using the right hand, and I'm gonna put the geographical east, which is the J direction. That is the one taken by the wire. And according to the chart, I need to have a magnetic field that has, let's start maybe from here, that has the X component negative, and the Z component that is also negative. And if you remember the very first activity, the beginning, the Z axis was pointing downward. That was the K positive. So now we do have a negative pointing upward, the BZ component. Therefore, our vector, let's say maybe in green, magnetic field will be this one in green. And because the vector is tangent to the loop, we imagine a circumference. This is what I do with my student. That's why I use this bracelet, because then they put the observatory and we imagine a loop. Let's see if I do have maybe for which this is a tangent. So there will be a loop here of the magnetic field. Possibly there can be also a circumference here where the green vector is tangent to both circumference. But in our group, Brian was saying the current has to be above the earth ground. So the current has to be above. This second loop doesn't really count. And for the right-hand rule to be true, we need to have an into the page current, which means opposite to the east direction, so west.
Oh.
Does it make sense?
Yeah.
Any questions so far? Okay, so then let's go into the last page. The last page has the same chart, but this time the timing is between 10 and 2 o'clock in the afternoon. Again, a student had to visualize the X, Y, and Z coordinate at 12:30. And here is the part that I had, just a picture to do the same thing that we did right now. So this question has the picture and also has what is the current, due north or due south? Did you discover that already when you were divided in groups? Because with Brian and Adam, we did it already. Or you wanna take time and also answer whether the current is north of the observatory or south of it? What do you would like to do?
Let's go back to breakout rooms for a few minutes. How's that?
Okay, just few minutes, and then we have to decide whether it's north or south. Thank you.
All right.
Welcome back. Anyone would like to share maybe perhaps the answers to whether the current is due north or south of the observatory? If you feel like. The sky north of the observatory, yes, that is right. And it is at this point that with my student, I ask them to show me the vector magnetic field on top of the observatory, so that they know that the current has to be not exactly above, but a little bit north of the observatory. Thank you. And here, this is a schematic that I just added for my student. It's not officially on the NASA HEAT handout, but at the end, in essence, the magnetic field B is here. And so the wire with current has to be west and a little bit also north, in the north direction. The wire, the electrojet is 100 kilometers above the Earth's surface. And the next page uses math. So the student will be asked to find first what is the distance north, this distance D, between the observatory and the line of the current falling down. And then, of course, they will need to find what is R, the diagonal distance between the observatory and the wire of current, so that they can use Biot and Savart to work backward from the wire magnetic field to find the current. Now they know that is west, they know that is north, they just need to find how much north and the amperes. So let me cancel this, and if you're okay with this, I will leave this last page to complete again in groups. So first, how far due north, and then do the math to find the value of the current. If it's possible, Chris, you can divide it back in our groups rooms.
And what, 5 or so minutes?
Maybe, yeah, between 5 and 10.
Okay, sounds good.
Thank you. Did we find some kind of numbers? Maybe the time was too short. In my group, we did it. Ryan drew on the page and we did everything. Would you like to share your numbers for the distance and maybe for the current if you have them? And if you want me, I can also draw and do the math quickly.
I found an angle which is, I mean, we can find the theta, which is around 63.5.
Mm-hmm. You were saying 63.5 an angle, right?
Yeah.
We had some variation in the answer depending on how you read the graph. Yes, it's something between 50 and 75 kilometers north of the observatory, indeed. In my chart, I have just placed the BX and the BZ, depend on how you read the numbers.
So just so I understand this, sorry to interject, the BZ and BX values are taken from the graphs in the document. Am I correct?
Mm-hmm. Mm-hmm.
Yeah. Okay. Thank you.
Yes. And it's not super straightforward. You just approximate just from the chart. So, for example, in my notes, then Brian had slightly different numbers, but I tell my student is okay. The procedure, the steps are more important. So I have for Bx, I have the 200, which is negative because it's in the negative direction, nano Tesla. And for BZ, I do have the negative 150 nano Tesla. And then let's say that in blue, I have here the wire with current. I need to draw the radius forming 90 degrees angle between the magnetic field vector and the wire with current I. Then I have the ground and the vector, and the current is at 100 kilometers from the ground. So in the group with Adam and Brian in our break room, we calculated the angle here using the arc tangent in between the vector BZ over BX. Sometimes I also do just a proportion.
Oh, okay.
The goal is to find D, the distance D. So maybe, let's see if I can just highlight in maybe, I don't know, yellow. You say that this triangle is similar either to this or the other triangle.
That's what I was doing, similar triangles, yeah.
Mm-hmm. So you can establish a proportion. For example, I say that they need varies, but I say that Bx is like to BZ, like the 100 kilometers is to the distance D. And so I find that D is, in my notes, 75 kilometers. So I use Bx over Bz. And I use this angle, which is the same as that. And the last part to find the current using Biot and Savart, mu0 times I divided by 2 pi times R. Student will need first to find the B. They have a X component and a Z component. So for B, they need to take the square root of the whatever X they had, in my case, let's say 200 squared and 150 squared. So they have the B total. And there is, again, a review of the vectors, the magnitude of a vector. And then also for R, because we have a D and we have 100. Yeah, matter interaction activity is a great, it is a great activity. I was telling to my group that I dedicate an entire time, and I meet the student for longer than 2 hours. So an entire day that we meet, the 3 hours, we watch some of the videos, we talk about the magnetic field of the Earth, they go with their phones, then they grab the Play-Doh. It is all everything on the day, but it could be just divided in little pieces. Just one day you do just one part, maybe. So also radius has to use the Pythagorean theorem, the 75 kilometers plus the 100 kilometers. 100 squared. And lastly, once they have the I current, using Biot and Savart, they need to be mindful to convert it into amperes. I want them to go back instead of nano Tesla to use Tesla, and instead of kilometers to use meters. So the current, if you then do the math with my numbers, is around 1.56 10 to the power of 5 amperes. but again, the numbers are not super fundamental. The activity on the bottom says that, I will gonna show it to you in a moment. It says, I'm just reading, although the data are plotted in nanotesla, you should find the current to be rather impressive in size. So this electrojet current, if this had been a stronger magnetic field disturbance for which the perturbation to the magnetic field could reach even 2000 nanotesla, the current responsible for such field will be approximately 1 million amperes. So it's amazing, huh? I know we are almost out of time, so I would like, if I may, Chris, ask first if you have any questions in regard of this activity.
I actually have a question. Would it be okay if I asked it right now?
Please.
So in the graphs that we had in this activity where we saw the nanotesla fields, I just have a quick question about the numbers to the right of those graphs. Those numbers, do they mean something?
Yes.
I have a conjecture, but I'd like to verify.
Yes. They are the actual magnetic field.
Good.
Yeah, that was your conjecture?
That was my conjecture. So that's the baseline value. And then what you have plotted are the deviations from that baseline value.
Yes.
Okay. And that's why the last plot, the F plot, makes sense, because the Z field is like the most dominant.
The most dominant, indeed.
Okay.
You're right. Yes.
Thank you.
You're welcome. So you can find more activities of the group if you just Google American Association of Physics Teachers and then NASA HIT. I will also have the link at the end, but this is the link. And the activities are all here. There are for kinematics and for optics, magnetism. Last year, I know optics did the eclipses also, because there was the eclipse in May, right? And also, one other thing that I would like to share with you is, give me a moment that I go back to the PowerPoint, if I have it here, is that any one of you, this was me at the workshop in June, you become again a student, and it was amazing.
We're looking at the web browser, actually, not your slide.
Okay, so let me share it. Sorry. Here, share. You have it, right?
Mm-hmm.
Yes. So if you also would like to, are thinking that you would like to become an ambassador, I put into, this is us, 8 ambassadors each year. And the Ramon Lopez, Professor Lopez, Rebecca Vieira, and then other members of the NASA HIT group, Jimena, Darsa, and Ambrose. But here in the last page, here there are some links, and here is some information in case you would like to become a NASA HIT ambassador, and you will be ambassador for about a year. You may fill out this form and send it to Rebecca Vieira. I will leave this with optics if it's okay.
Absolutely.
Do you have any questions perhaps? And I guess it's almost time for optics to take over, right?
We have a couple of minutes if anyone else has questions. Otherwise, we'll wrap up.
able to give us links to all the resources that were used here, or is the Word file all that there is?
The link that Chris Louis placed on the chat guide us to the all resources that the group has
thank you.
prepared. You're welcome. And also, if you look at the resources, if you click on each resource, maybe let me, share one more time. If you click on each resource, like for example, magnetism here, you
I see it.
there are different activities, and for each activity you have the file. But also, if you click on the DigiKit, you have many other information.
That's beautiful. Yeah, thank you.
That
Thank
can
you.
help for the entire preparation and for the
Thank
class.
you. Yeah.
You're welcome.
And as we draw to a close here, I'm going to put the URL for optics evaluation. We would very much like your feedback on this workshop as we take that seriously. And we would like you to do this quick survey about this workshop. This was amazing. This was an amazing, and I even learned of a few new resources that I didn't know about. So I can see lots of applications for this.
Yeah, the group is amazing, and their activities are great. Sometimes the first impact is, whoa, it's too challenging. But in reality, they are not. My idea is that they flipped our perspective. Like this one, usually we do a current wire and what is the magnetic field at the point P. And here they flip it. I give it a magnetic field and tell me what's the current.